So here's something that most people don't think about. When you call GPT-4 or Claude or Gemini, someone on the other side is paying for a GPU to run that for you. And GPUs, as we know, are pretty expensive. And we're talking thousands of dollars per hour for a single high-end cluster. Now multiply that by millions of requests per day, and you start to understand why inference cost is maybe the defining engineering problem of the AI era right now. And today we are getting into exactly how companies like OpenAI, Anthropic, Google, how they actually solve this. Now, before we get into solutions, let's make sure we are aligned on why this actually is hard. When you run a bad job, that is training a model, processing a data set, you can throw everything at it in one shot. Throughput is all that matters, but inference is different. A user is sitting there waiting, and you have a latency budget. And the model itself is enormous. Something like a 70 billion parameter model is like 140 gigabytes in float 16. Just loading that onto GPUs is a whole thing. So the challenge is serve this giant model to millions of users fast and without going bankrupt. So that is a problem. Now let's talk about how you actually solve it. Okay, so this is the one I think is most underappreciated. Inside a transformer, every time you generate a new token, the attention mechanism needs to look back at all the previous tokens. Without any optimization, you would recompute the key and value matrices for every single previous token every single time. So that's quadratic in sequence length, and which is also very brutal. The KV cache solves this by just storing those computed keys and values. So you compute them once, cache them, and on the next token you just read from cache instead of recomputing. This is why inference isn't as slow as it could be. But, and this is important, KV cache takes up GPU memory and it takes up a lot of it. So for long context, the cache can be bigger than model weights themselves. So now you've got a memory management problem on top of the compute problem. Here's a problem that's kind of subtle but has a massive impact. In static batching, which is the naive approach, you bundle a fixed set of requests together and process them as a batch. The problem is that different requests generate different numbers of tokens. Some finish early and some finish a little late. The GPU just sits there waiting for the slowest one in the batch to finish before it can start anything new. Continuous batching, on the other hand, also called as the dynamic batching or iteration level scheduling, fixes this by letting new requests slot in the moment a slot opens up. You're essentially treating the batch as a live, fluid thing rather than a fixed group. Orca, the paper that popularized this, showed you could get 36x better throughput with this single change. That's not a 10% improvement, that's completely a different order of magnitude. So continuous batching keeps the GPU busy. Good. But what if the model is just too big to fit enough of it in memory to batch efficiently in the first place? That's where quantization comes in. Neural networks weights are stored as floating point numbers, typically as float 16, which is 16-bit per parameter. And quantization is the idea that you don't actually need that much precision. You can represent those weights in 8-bit integers or even 4-bit, and the model still works almost as well. Why does this matter? Because a 70 billion parameter model in float 16 needs about 140 gigabytes of GPU memory. In a 4-bit, that's down to around 35 GB. That means a model that previously required multiple A100s, which cost thousands of dollars, can now run on a single consumer GPU. The quality drop is real, but it's often surprisingly small. Techniques like GPTQ and AWQ have gotten really good at choosing which weights to quantize more aggressively and which to leave at higher precision. So in practice, you can get most of the memory savings with very little of the quality degradation. Now, this one is genuinely clever. The problem with LLMs is that they are autoregressive. That is, you can generate one token, feed it back in, generate the next, and repeat. You can't parallelize across tokens because each one depends on the previous one. Speculative decoding works around this by using a small, fast draft model to speculatively generate several tokens at once. Then you run those tokens through the big model in a single forward pass to verify them. If the big model agrees with the draft model tokens, which it often does, especially for predictable or common sequences, you get multiple tokens for roughly the price of one. If the big model disagrees on a token, you discard everything from that point and restart. In practice, you get around 2 to 3 times speed up on many workloads. Google uses a version of this called Medusa. DeepMind has its own variant, and it's becoming standard at the infrastructure level. Now, what if the model is just too big to fit in on a single GPU, even with the process of quantization? This is where model parallelism comes in, and there are two main flavors for this. Tensor parallelism splits individual layers across multiple GPUs. That is, you literally cut the weight matrix in half and put each half on a different GPU, then synchronize everything during computation. This is fast but requires high bandwidth interconnects between GPUs. On the other hand, pipeline parallelism is a bit different. That is, you put the first half of the model's layers on GPU 0, the second half on GPU 1, and pipeline requests through like an assembly line. This is better for higher latency tolerance, but it also introduces pipeline bubbles. Most production systems uses the combination of both, and often a third kind called data parallelism, that is running separate model replicas in parallel to handle more concurrent users. Now here's the one that's particularly relevant if you're building on top of LLM APIs. In most applications, you have a system prompt. Maybe it's long, maybe it has context or documents or instructions. Every single user request has that same system prompt pre-printed. If you're not caching the computer representation of that prompt, you're paying to process those thousands of tokens every single time. Prompt caching, which Anthropic, OpenAI, and Google all offer now, solves this by caching the KV activations for common prefix. Subsequent requests that share that prefix skip the computation entirely and pay a much lower cache rate price. In some workloads, this can cut costs by around 90%. It's a trivially easy optimization that a lot of teams are still leaving on table. Now coming to the frontier stuff, that is what the best inference systems are moving towards right now. Here's the insight. The two phases of inference are fundamentally different workloads. The prefill phase, that is processing of the input prompt, is compute bound and highly parallelizable. The decode phase is like generating tokens one by one and is memory bandwidth bound and sequential. Now running them on the same hardware means you are always underutilizing something. Disaggregated prefill decode separates these into different server pools, each optimized for its specific workload. DeepSeek's inference infrastructure uses this. It's more complex to orchestrate, but it's meaningfully better in resource utilization. You'll start seeing this become the standard for large scale deployments over the next couple of years. Now let's zoom out and look at how all of these pieces fit together in a real system. At the top, you've got a load balancer that also does continuous batching. That is, it decides how to group incoming requests to maximize GPU utilization. Below that, you have your inference servers, that is usually something like vLLM or NVIDIA's tensor RTLLM, running your quantized models across multiple GPUs with tensor parallelism. The KV cache layer handles both paged attention for memory efficiency and prompt caching for repeated prefixes. At the bottom, your model weights are stored in quantized format, like int4 or int8, to minimize memory footprint. So none of these optimizations is optional at scale. You need all of them working together. Companies like Together AI, Fireworks AI, and AnyScale have built entire businesses on getting the stack right. Now, here's the wild thing. The cost per million tokens has dropped by something like 100x in the last 4 years. And that's not because the hardware got 100 times cheaper, it's because the inference engineering got dramatically better. Everything we covered today, that is KV caching, continuous batching, quantization, speculative decoding, page attention, these are engineering decisions that compound on each other. The next wave is going to be about mixture of experts routing, where you only activate part of models per request, deeper hardware software co-design, and eventually running these models at the edge, like on your phone without a server at all. So this is one of those areas where the gap between the best teams and the average teams is massive, and it's only going to widen. If you work anywhere near AI infrastructure, this stuff is worth understanding deeply. Alright, so that's a wrap on inference optimization. If this was useful, subscribe the channel for more such videos. Thank you.